Database systems rely on three key structures: tables, views, and materialized views. Each serves different purposes in managing data efficiently. Tables are the foundation of database systems. They store raw data physically on disk or in memory, providing direct access through reads, writes, and indexing. Tables excel in online transaction processing and primary data storage. Views are virtual structures created from one or more base tables using SQL queries. They don't store data physically, but act as named queries that compute results dynamically when accessed. Views offer data abstraction, security by hiding columns, and reusability without duplicating data. Materialized views are pre-computed snapshots of query results stored physically, similar to tables but derived from base data. They require periodic refreshing to stay current, but provide much faster query performance by avoiding recomputation, especially for complex aggregations. This comparison highlights the key differences between views and materialized views in terms of data storage and access speed. Performance varies. Tables offer high speed for direct access, but can degrade with complex operations. Views provide fast access for simple queries with no storage cost. Materialized views deliver rapid query times after refresh, but incur storage and compute costs for maintenance. This diagram shows how data materialization works, transforming source data through SQL queries into a materialized view that can be quickly queried. Choose based on needs: tables for foundational data and transactions, views for flexible abstractions without performance penalties, and materialized views when query speed is critical in analytical workloads. This flowchart illustrates SQL query execution order, showing how different operations are processed. Understanding query flow helps in choosing the right database structure for your needs. Tables form the foundation of database storage, holding raw data in structured rows and columns. Tables are the fundamental building blocks of a database, physically storing raw data in rows and columns. Tables physically store raw data in a structured format, with rows representing records and columns representing attributes. Direct reads and writes occur on tables, supporting frequent access and online transaction processing for real-time operations. Table performance depends on indexing for fast lookups, partitioning for scalability, and underlying hardware for processing power. Tables form relationships through primary and foreign keys, as shown in entity relationship diagrams. Storage costs include space for data and indexes, with additional compute costs for tasks like vacuuming and optimization. Tables serve as the core of data storage and systems, feeding into operational and informational environments. Tables are essential when data freshness matters most, ensuring real-time access for critical operations. Views are virtual tables created from SQL queries on one or more base tables. They provide abstraction, security, and reusability without storing data physically. Views are virtual tables created from SQL queries that reference one or more base tables. They don't store data physically, but act as named queries executed each time they're accessed. Views provide data abstraction by simplifying complex queries, security by hiding sensitive columns or restricting access, and reusability without duplicating data. They have minimal cost, only requiring query execution time. Use views for data abstraction, security to protect sensitive information, or simple derived queries. Unlike materialized views, they offer instant updates but may be slower for complex computations. Materialized views are pre-computed snapshots of query results, stored physically like tables. They trade storage space for faster query performance by avoiding recomputation. Materialized views are pre-computed snapshots of query results, stored physically like tables. They trade storage space for faster query performance by avoiding recomputation. Materialized views excel in scenarios with expensive aggregations, such as SUM or AVG over large datasets. They provide sub-second query times after a refresh, but require time to update, potentially causing staleness. Performance gains are significant in read-heavy workloads, like dashboards or reports. Performance trade-offs involve balancing query speed with data freshness in database systems. Let's examine how tables, views, and materialized views handle this balance. Tables provide the foundation of data storage, offering high performance for simple queries. They store raw data physically on disk or in memory, allowing fast access through indexing strategies like B-trees or hash indexes. This makes them ideal for direct reads and writes in transactional systems. However, performance can degrade with complex joins or aggregations over large data sets, as they require recomputing results each time. Views act as virtual tables, computing query results on the fly without storing data. They're ideal for lightweight queries and provide real-time data access, making them suitable for ad hoc analytics or data abstraction. However, for complex computations involving multiple joins or aggregations, views can be slow as they execute the underlying SQL query each time they're accessed, leading to higher latency compared to pre-computed options. Materialized views store pre-computed snapshots of query results, providing the fastest performance for complex aggregations like sums or averages over large datasets. After an initial refresh, they offer sub-second query times, making them excellent for read-heavy workloads such as dashboards or reports. However, they require periodic refreshes to update the data, introducing a trade-off where speed comes at the cost of potential staleness. The core trade-off centers on speed versus freshness. Tables offer the freshest data but with variable performance, fast for simple queries, slower for complex ones. Views provide real-time data access, but can be slower due to on-the-fly computation. Materialized views deliver the fastest query times for complex operations, but may contain slightly out-of-date data until refreshed. Choosing the right option depends on whether your use case prioritizes immediate data accuracy or rapid query performance. To visualize the materialized view process, consider how data flows from tables through computation to stored snapshots, as shown in this diagram. Query optimization plays a key role in performance. Factors like indexing strategies and query structure influence how tables, views, and materialized views perform under different loads. Real-world examples demonstrate how tables, views, and materialized views are applied across different industries, each chosen for specific performance and cost needs. E-commerce companies like Amazon use materialized views for real-time inventory dashboards. By pre-computing aggregations of sales data across millions of products, Amazon reduced query latency by 50% in their Redshift data warehouse. While storage costs increased by 15%, this optimization saved over $2 million annually in compute costs, demonstrating the value of MVs for read-heavy workloads. Media streaming services like Netflix leverage materialized views for user preference analytics in their Snowflake environment. By refreshing data hourly through incremental updates, Netflix achieved a 40% faster recommendation engine, enabling personalized experiences for over 250 million users. This approach balances performance with manageable refresh costs, highlighting MV's role in real-time personalization. Financial institutions such as JPMorgan Chase use views for ad hoc regulatory queries, providing secure, on-demand access without storing data. For predictive fraud detection, they employ materialized views on transaction data, cutting anomaly detection time from minutes to seconds and preventing over $1 billion in potential losses. This hybrid approach combines flexibility with performance. Healthcare providers like Mayo Clinic use tables for storing patient records, views for anonymized queries to ensure privacy, and materialized views for aggregated research data in BigQuery. This hybrid approach improved query performance by 60% for genomic studies, with automated refreshes providing cost savings. It illustrates how each tool serves specific security and performance needs. These examples demonstrate the diverse applications of tables, views, and materialized views across industries. Each tool is selected based on specific performance, cost, and data freshness requirements, enabling organizations to optimize their data strategies effectively. Emerging trends in database optimization include automated materialization, where artificial intelligence automatically creates and refreshes materialized views based on observed query patterns. This automation uses machine learning to predict usage patterns and optimize refresh schedules, potentially cutting costs by up to 30%. Platforms like AWS Redshift now support Delta-based refreshes, integrating with streaming data to enable near real-time updates. This integration helps predict which queries benefit most from materialization, improving efficiency in machine learning workflows. Streaming data from IoT and event-driven systems drives this evolution, with intelligent MVs using advanced algorithms for self-management.